from three people who are actually bringing these devices to you. And there was a lot of comments yesterday about how FPGAs aren't going to move into cell phones anytime soon. And our first presenter, John Birkner, is going to tell you why that is not going to hold true. John has been, is now at SiliconBlue, and before that he was at Xilinx, QuickLogic, and MMI. He apparently invented the PAL device, something I did not know, and he wrote the first version of PALASM, which is something that I used when my hair was still actually brown. So with that, I'll turn it over to John.
Has built from ground up an SRAM-based FPGA that is single chip, and it's targeting handheld devices. You might wonder, how can you put an FPGA in a handheld device? Well, prior to SiliconBlue's product, FPGAs just haven't addressed this marketplace. So the first requirement in a handheld device really is power. It has to be low power enough not to run your battery down. It has to be low cost so the consumers can buy it. It has to be a small size. You can't put big packages in your handheld. And the advantage is time to market. So when I approach manufacturers of these handheld devices with my product, they say, well, my application processor does everything I need. Why would I need an FPGA? And well, then what happens is one of his competitors comes out with a product. Instead of having one camera, it has two cameras. So he needs to quickly shuffle and figure out a way to add another camera. His application processor may not be able to support that. Enter SiliconBlue. Another thing that's happening is pico projectors. So the application processor may not have an interface to a pico projector. And we can go on. You might want another display. Cameras have two displays now. Samsung recently came out with a camera. I remember my daughter, the first thing she did with a digital camera is take pictures of herself and her friends. Samsung now has a camera that has a cell phone that has two displays and two cameras, so you can do exactly that. Take a picture of yourself. Who needs it? Well, the kids love it. And how is Nokia or LG going to respond to that? Well, they're going to scramble and try to get there as quick as they can. So other features, keyboards, mobile devices now have more than one keyboard. Multi-format flash media. Flash media is always improving standards, increasing density. So this is why you might use an FPGA in a handheld device. What architecture is suitable for a handheld device? Well, the first thing you need is really low power. So when we cleaned the whiteboard and started from scratch, power was our first concern. How do you design an FPGA that has really low power? And in the 20 or 30 years of my experience, the circuit designers have been constantly trying to improve performance and at the expense of power. So to design an FPGA that is low power is just kind of counter to all of their experience. So starting from scratch, we ask, well, how can we do this? And we picked an architecture that was very similar to the very successful SRAM-based FPGAs. And the SRAM FPGAs have really won the battle in the last few decades by being able to be on the leading edge process node to get the best performance and the highest logic density for the lowest cost at the expense of power. So how do we get the power down? Well, we decided to go on the 65 nanometer LP process from TSMC, and that was really the first process node where LP, low power, was the lead process node. So that was a good opportunity then to get low power. So TSMC had a library and offered a number of transistors for us to choose from. We chose all the high VT non-leaky transistors, and at the expense of performance by about a factor of 2. But we got the leakage down to, for 4,000 logic cells, about 15 microamps in static mode. So this FPGA is an array of programmable logic blocks with block RAMs, and 4 banks of I/O. The first 3 banks are a standard I/O, and the third bank is an LVDS MDDR bank. The RAMs are 4K bit blocks. The programmable interconnect is pretty standard. I'll go over that. And we also chose the high VT transistors for that interconnect, except where we needed some performance, then we would use the standard VT and burn a little power, but design in power down circuitry. So initially, you power up the FPGA, it's configured for minimum power. And things like the carry tree or a fast clock, you can configure those devices to use the standard VT transistors and thereby burn some power. Okay, we have a fast carry tree, and we included a non-volatile configuration memory. So different than the standard SRAM FPGAs, we do have a configuration PROM on board. And we were able to do that with a recently available non-volatile technology that rides on the leading edge process node standard process with no process tweaks. This is a significant advantage to be able to have a non-volatile memory that is on standard process compared to a number of FPGAs in the past have been anti-fuse or flash, exotic kind of processes that keep the architecture 2 or 3 process nodes behind the leader. So the lead process, standard CMOS, 65 nanometer, 40 nanometer, moving to 28 nanometer. It takes a while for flash to catch up. It lags 2 or 3 nodes behind. So we have a non-volatile technology that is on the leading edge process node. The advantage there is single chip. So in an SRAM FPGA, you turn the power on, you configure it, it does the logic function, and then you turn the power off, it goes away. So turn the power back on, you have to reconfigure it. Externally from an external serial flash, SPI flash for instance, or from a processor memory. There's a lot of advantages to configuring your logic from an external source for debugging, system bring up, for field edits, a lot of advantages. However, we have found in the mobile applications, the ASIC model is highly preferred. Customers want to buy a chip that has a function and be done. So the non-volatile configuration memory then allows the FPGA to be shipped like an ASIC, programmed at the foundry and shipped as an ASIC. So this is the basic FPGA architecture. And looking at the programmable logic block, 8 LUTs and registers, 4 LUT, standard 4 LUT register with the bypass, and common clock, enable, set, reset, carry logic. Carry logic propagates a carry in about 0.2 nanoseconds. So you can get 16-bit kind of arithmetic functions running at 200 megahertz or so. We also use the carry train as a delay line. It's a very constant delay line. Okay, so this is a familiar architecture supported by existing synthesis tools from Synopsys and others. The block RAM, we picked an off-the-shelf register file from the TSMC library. It is a 4K memory block, 16-bit wide, 8-bit address, a nice block to do register files, FIFOs, whatever you want to do with a RAM. It also initializes on power up, so it can be a ROM lookup table. It's very fast, and it consumes a half a microwatt, really low power, runs 200 megahertz, very nice memory. This is a really good time to start an FPGA company. SiliconBlue is about 3 years old. We started in 2006, and at that time, the TSMC LP65 LP process just becoming available. Really good timing for us. And there's a lot of IP available. This is a standard IP. Compared to the incumbent FPGA manufacturers, they handcraft a lot of their circuitry, and they're all billion-dollar corporations, but we were a startup that could take advantage of the IP off the shelf. Likewise, the I/O, we picked the I/O off the shelf, and these are very small ASIC I/Os from the TSMC library that on the first 3 banks, standard ASIC I/O drives 8 milliamps, 12 milliamps, 16 milliamps, depending on the voltage, and each bank can have a different voltage, 1.2, 1.5, 1.8, 2.5, 3.3. In fact, FPGAs are very good at voltage level translation. Let's say your application processor is running at 1.8 volts. You want to hook it up to a 3.3 volt memory, drive it through an FPGA. So one side of the FPGA will be 1.8 volts, the other side will be 3.3, and it's a voltage translator. Very common application. So we have a standard I/O with some registers. We can perform DDR in this block. We also have what we call an ICE gate, a control line on a bank that you can inhibit signals coming in from going up and down. Let's say you're hanging on an address bus, but you're in a power down mode or an idle mode. You want to stop the burn of those address lines going up and down in your chip, driving capacitance and burning power. So we have an ICE gate line. That's one of the features. And we support many standards, LV-CMOS. And the left bank is actually a TSMC mobile DDR, MDDR driver. And it also supports differential inputs and outputs, LVDS at 2.5 volts or 1.8 volts. Okay. So programmable interconnect, each PLB, programmable logic block with 8 logic cells in it, can control and observe all of the surrounding neighbors at around 200 megahertz. And then we also have span 4 lines, which each line here is a group of 48 wires, which permutates on a basis of 12. So every 12th line can do a right angle turn here to go up or down. And notice the RAM 4K, being 16-bit wides, fits in the, it matches 2, in the same pitch as 2 programmable logic blocks. So that makes the routing convenient, eases the software tool burden. And then we also have span 12s. So there's going to be 24 lines in each group, which permeate every 2. So a 12 span can make a right angle turn. 2 of the 24 can make a right angle turn, and then that precesses across. So this is a fairly standard FPGA architecture with global routing resources, 8 global resources, which can be powered down. And they can be used for sets, resets, clocks, enables. So I mentioned the non-volatile configuration memory. So this is the first SRAM FPGA with a onboard configuration memory on chip. And we can configure in 25 milliseconds or so from the onboard non-volatile configuration. It's secure, and once it's programmed, you can program the last fuse, which says you cannot read it out anymore, which makes it secure. So what you essentially have is an ASIC. So you power up this FPGA, it configures itself, and then it doesn't allow reading of that non-volatile configuration memory. That configuration memory also configures the SRAM blocks, so they can be ROM or program store, lookup table, whatever. So I mentioned we use the TSMC LP standard process. This gives us the smallest die, lowest cost, and allows us to ramp up rapidly. We have a standard set of design tools. Verilog and VHDL are the inputs, and we have a timing-driven synthesis from Magma, supported on Windows or Linux. We have power analysis tools, management tools. We have a Excel power estimator. You can download these tools and try it out for 30 days for free. This is a power consumption benchmark. It shows power versus the clock frequency in the range 0 to 50. Now that might sound, well, that's not very high performance, 50 megahertz, wow. But in your handheld, around the periphery of your application processor, that's about what things run. And we have applications going up to 120 megahertz. Let's see here. So looking at the ICE65, ICE being the name of our FPGA, you can see at 32 megahertz, which we actually spec on our data sheet, was about 10 milliwatts. Compared to the next competing FPGA on the 130 nanometer process, for this benchmark of 3,500 LUTs at a toggle rate of 12.5%, the 130 nanometers is running about 3x in dynamic power. And this is what you would expect. You've got more capacitance, 2 nodes, 2 process nodes back. And now here's a 65 nanometer SRAM FPGA, and it's burning a lot more power. It does have the same slope as you would expect. We're both on 65 nanometers, same capacitance per node. But look at the origin. It's 35 milliwatts. 35 milliwatts will run down your cell phone in a few hours. So clearly, You can't take an off-the-shelf SRAM FPGA and put it in your handheld. It doesn't compute. CPLDs have made some footholds in mobile handheld, mainly because they are some of them are zero static power. And however, the dynamic power is really high. First of all, they're on 130 nanometers or 180 nanometers. Also, the CPLD, all inputs coming into a CPLD go to all possible target logic blocks through arrays, and whenever an input is toggling, it's swinging a vertical and a horizontal wire across the whole chip. So inputs in a CPLD burn a lot of power. Compared to an FPGA, everything is segmented, local routing. And if we look at the node here, if I blow this up, you can see SiliconBlue is down here in the 50 microamps. Actually, it's more like 15 to 25. I was conservative when I ran this original benchmark. Compared to the next FPGA is up there, 150 microwatts, and this is a microwatt. The CPLD also hitting 150, but at this increased slope. And then here's another example of a CPLD up there. So these are kind of within the handheld range, but the ICE chip is showing the best performance for handheld. Actually, we almost over-designed our power. Most of our applications, 50 or 100 microamps is fine. Your battery, your cell phone battery can run a few months at that level. So we have a family of devices ranging from a 2,000 LUTs to 16K LUTs, and IOs ranging 128 to 384. Embedded RAM bits from 64 to 384, and really low power, sleep currents ranging 3 to 50 microamps. Dynamic current at 32 kilohertz is one of our benchmarks, 32 kilohertz. All of our evaluation kits run at 32 kilohertz. And that's sort of the base time in handheld. And so we're at 15 through 75. And then our dynamic current, this example, 60 milliamps, or 6 milliamps. These devices available, and now we're just getting into production and shipping our first production from TSMC. We have a range of packages. Packages need to be small and mobile. This is a huge package here. The VQ100 is popular, especially in Asia, because they like to have 4-layer PC boards, low cost, and the 0.5 millimeter pitch here, where you can see all the pins, is popular. But it's a big package. That is 16 by 16 millimeters, actually 14 by 14 body. One of our most popular packages is a 12 by 12. Notice the grid here. It's on a 0.5 pitch, but it's sparsely populated. And this eases PCB design. We actually have app notes that show how you can lay this out on a 4-layer PCB, which is popular in Asia. So, time running out here. Packages range down to 3 by 4. And this is a wafer level chip scale package. And notice there's 2 pitches here, a 0.4 and a 0.5. I've always asked myself, why has it taken so long to get these really low-cost packages? Well, they're really not a package at all. It's just a die, a bare die with balls on it. And I think we're going to be seeing a rapid change here in the direction towards these wafer-level chip scales, because the package is is so low cost. Those other packages I showed you, they can cost $1, and that is much more than the die cost. So what's wrong with this picture? So why hasn't everyone converted to wafer level chip scale? Well, there is an issue here. How many balls can you get on the die, especially if you want a low-cost die? So what we do is we put an RDL, redistribution layer, and then we lay down the balls. And this package costs 5 cents compared to $1 for those other plastic packages. We also sell die. And Chuck asked me, well, hey, it's really hard to read this. Can't we make this bigger? Well, the point of showing the data sheets was we want to sell die. We show you our die, and we'll give you all the parameters to build this die. This is showing that between application processor spins, which are 2 or 3 years, stacking a die allows you to add features to your SIP on a much more a quicker basis. IP is really important, especially in the Asian market. A company like Cisco here, if you sell FPGAs to them, you'll never know what they do with them. But in Asia, they don't even want to buy our tools. They don't want our tools. They want us to custom design their applications. So we have a big applications team, and we use this IP library then to actually build ASICs for the handheld manufacturers. So I've run over my time here by about 30 seconds. In conclusion, SiliconBlue is the first with a mobile FPGA. The market is growing fast, 50% according to iSupply, and it's a very exciting market. Thank you.
Thank you, John. I think we have time for a few questions from the audience.
Any questions?
Hi. What is the on the die? What's the smallest part and the largest part? What is the size of the die, and how many IOs are actually on the die itself?
Our smallest die is 2.5 by 2.5 millimeters. Largest die is 5 by 5 millimeters. And the IOs, they go as low as 48 IOs on our wafer level chip scale package, all the way to 277, I'm sorry, 176 on our largest package.
Yeah, but just the die itself, what's the maximum IO on the die itself? Is that 176?
No, actually on the largest die it's 384 IOs.
So if you took the bare die, you'd have 5 mil by 5 mil with
correct.
500.
And we're on dual rank, staggered pads. I think it's 40 mil pitch, 40 micron pitch.
And you might not be able to answer this one, but on your CPLD comparisons, I've always seen a lot of press from Actel on their Igloo parts. How do you compare with the Igloo parts from Actel?
Actually, one of those lines there was an Igloo, and we're 1/3 the dynamic power and 1/3 the static power. You have to look at the specs for power down, so we really promote what's happening at 32 kilohertz. That's the heartbeat of handheld, and we're at the 25 microamps at the heartbeat.
Very interesting. Well done.
Thank you.
Jeff Beard from BDTI. What can you tell us about the selling price of these chips?
They range $1 to let's see, $9 in high volume, million unit quantities.
Thanks.
Minjin from UC Berkeley. Recently, like Actel, another FPGA company, they rolled out ultra low power FPGAs.
Yes.
They claim 30,000 system gates, they consume like 2 microwatts. And my question has twofold. The first one is, have you ever compared the performance in terms of power consumption with their products? Secondly, if there are obvious advantages of using SiliconBlue chips, and in your opinion, what's the fundamental difference there?
In my opinion,
what's the fundamental difference in terms of circuit design, architectures, or something else?
Okay, good question. I'll go in reverse order. So fundamental difference, we're on the 65 nanometer, Igloo is on the 130 nanometer. We have a standard SRAM-based architecture. They have a flash-based architecture. We're on the leading edge process node and we'll always be there, so we'll be the lowest cost. And you have to watch marketing. So they advertise X zillion gates at 2 microwatts. Well, if you really look at the data sheet, the 2 microwatts is on the 500 gates. And there'll be a lot more power. That's why in my benchmark, I normalize to a certain number of logic cells. And that benchmark is a standard benchmark for 30 years in the programmable logic industry. We fill up the chip with 16-bit counters, and the average toggle frequency on a 16-bit counter is 12.5%. And we run the power estimator, we put it on the bench, and that gives us some figure of merit of power.
Okay, let's take one more question.
Hi, Fianato Wally from Intel. So the larger package you described, you said is routable in 4 layers on the motherboard. What are the design implications of moving to the smaller packages? Does it require HDI, or do you just need more layers in a standard PCB?
So if you look at the cross-section of the PCB in your iPhone, it'll be a 12-layer board. In Asia, many of their applications, their low-cost applications, they're only doing 4-layer boards. In Taiwan, they're doing 8-layer boards, and it comes down to the pitch. So the ball grid array, or the ball grid pitch in China, it's got to be a millimeter. In Taiwan, it's 0.5 moving to 0.4. And in the US, it's also, we're in an underdeveloped country here. It's a millimeter here. So Taiwan is leading with the 0.4 pitch. And as soon as we flip over to the 0.3 millimeter pitch in 2011, the number of balls that you can get on a die is going to really compete with the number of balls you have in a package. So packages may vanish. I may have missed one of your questions again.
Oh, so I was also asking about the impact to the board technology. Is HDI required, high density interconnects, in addition to more routing layers, period?
So I think you're referring to the serial connections, and we support the LVDS. And there's a trend in mobile. They have their own standard called MIPI that runs at 800 megabits moving to over a gigabit. And these are differential pairs running at a very low voltage, swinging around 1.25 volts. And one of the main drivers there is on your cell phone, the clamshell. When you open it up, you want to minimize the wires going across there. So converting to a serial standard is happening. On the PCB, actually packages, ball grid array packages are PCBs themselves, the substrate. And so we see a convergence with the PCB substrate and the iPhone PCB substrate. They're converging to the same technology. So why put a PCB on a PCB? Let's just go and put balls on the chip and flip them over to the cell phone PCB.
Okay, thank you, John.
Thank you.
In addition to apparently reconfiguring the building, Stanford is trying to get rid of us, and they have asked me to announce that the coffee will be leaving imminently. So if you need a final caffeine fix, now is the time. Our second speaker today is Dan Mansur from Altera. Dan is running the technology office responsible for research at Altera, and he's made many contributions over the years to the Stratix and the Cyclone products definitions. Previously, he was with PMC Sierra when he was responsible for the marketing applications in the microprocessor division. So please welcome Dan.
Well, it's tough to compete with coffee, so I'm glad you're still here. Once again, good afternoon. My name is Dan Mansur. Last year, I was here and we discussed Stratix 4 and announced Stratix 4. It's been about a year. We've had that product out for a year. And today, I'll be talking about two new families. I'll be talking about Stratix 4 GT, as in enabling 11 gig, and I'll be talking about driving the cost down on FPGAs to half the power, half the cost. So first of all, I just want to kind of go back a step and talk about Stratix 4. It's in 40 nanometers. We've been shipping it for a year. The 11 gig availability has been the last 6 months. It has 2.5 million transistors. To my knowledge, that's the biggest or the most amount of transistors on a piece of silicon, at least from TSMC. Yesterday, to put that in perspective, it was discussed that Nehalem EX was 2.3 billion. So a lot of transistors, mass production. This device has full redundancy across the entire array, very similar to DRAM or SRAM. We also have ability to down bond and take any defect densities out of the I/O region. So the manufacturing is very high. We have high yields in this today. So the two products we'll be talking about will be going from the device you just saw, Stratix 4 GX with 6 and 8 gig, and moving to GT with 11.3 gigs. In addition to that, we've also last time talked about hard copy. Hard copy is the ASIC or structured array shadow of the product, where you can actually take your FPGA and you can move it to about 70% less in cost and still keep all the performance elements of Stratix 4. Now, if you really want in-field reprogrammability, then you'd actually move down to Arria 2GX. And Arria 2GX is being able to take the same basic fabric. We took all the cost out of, particularly in the I/O region and on the package technology, although still flip chip, a very low-cost flip chip, and able to get that into a higher volume, lower cost, lower power footprint. Together, this represents about 15 to 20 die, all mask layer changes, and about 30 to 40 different die package combinations. So that's 15 to 20 mask sets, if you will, at 40 nanometers. About half of them are out already. Okay, so looking at the GT, once again, that's 11.3 gig. It has up to 48 transceivers. Not all of them are 11.3 gig, 24 of them are, but certainly you can get 100 gig in and out of the device. It has superior quality. It has up to 6 PLLs per quad, and they can all turn on at different times. It has ring oscillators and LC tank. And I'll talk about how we actually utilize all those to be able to get the best jitter for the exact standard you're looking for. It's kind of the Swiss Army knife of a quad for 11 gig all the way down to 0.1 gig. And I think the innovations within the FPGA industry is really doing a lot of things to make that highly configurable both on a static basis and a dynamic basis. And I'll talk about some of the details there. This particular family, because it is 11.3 gig per transceiver, we're focused obviously on 40 gig, 100 gig systems. And I'll go through a lot of the IP that's available for that, both with our customers and with our partners. But certainly that's a market where it's difficult to develop an ASSP because of the volumes. The big three, they do custom ASICs, and the rest of the market, where you may have some differentiation or some quality of service that you need to do, FPGAs is a beautiful place to be for that. And then lastly, I'll talk about the IP boards and solutions and some of the products that are already available today in the market, showing 11 gig. So here's the family. I broke it down between the 40 gig and the 100 gig. There's multiple configurations for how many transceivers you need or how many user I/O you need. Each of the user I/O today does DDR3, DIMM support, full 1 gig per pin. We are innovating there. We're going to be bringing it up to 2 gig per pin. So that I think it's a scalable architecture that can go from 1 gig to 2 gig per pin for the memory interconnect. Certainly, memory is going to be a bottleneck. The transceiver, excellent performance. We meet all the standards needs, which I'll show you in a second. This obviously shows a typical eye diagram with 11.3. The part that I think is interesting here is, random jitter is not very much of the component, but now we're talking femtoseconds. That's 1/millionth of 1/billionth of a second. I didn't think in my career, we used to argue about picoseconds. Now we're actually talking about femtoseconds, which is just phenomenal. We're all going to be dealing with anyone doing 11 gigs, so we're not unique to that. But we break down all the jitter components. Random jitter is usually kind of a smaller components, deterministic jitter that you really have to break down because our customers actually have deterministic jitter that's dependent on their systems. So I think a lot of the innovation I'll be showing is the ability for us to break down those jitter components, isolate them, and accommodate them in system, in your actual system, your actual backplane. And the ability to test these products, I think some of the more innovations coming to be able to show what your bit error rate's going to be able to tune the equalization pre-emphasis standards, and to be able to optimize for your specific backplane. We're almost building a tester of those transceivers on the FPGA, if you will. And actually, our biggest customers or our first customers are obviously the test industry. A majority of our initial customer designs are actually for testers, and I'll talk about that in a second. This just shows one example relative to the OFI standard, CEI. And you can see that the various telecom jitter mask that you have here, this is a jitter amplitude over frequency. And of course, you want to be above that so you can actually tolerate as much jitter as you possibly can. And actually, it's good that the clock source is also helping us on the jitter budget because it's all about jitter budget. The higher the budget, the more you can relieve yourself into trying to get your design done or your particular chassis, your particular nuance in your backplane. So this shows you that we have excellent performance over that frequency range and meet and exceed the standards. Now you have to turn all the channels on and still show that jitter performance, not just one channel. Here's another example where, once again, we turned on all the transceivers, or at least in this case, it's 6 transceivers. We had to go through 100 meters of cable, and we showed the OFI SFP plus performance. Once again, excellent jitter performance and meets a beautiful eye. That's after 100 meters. Yeah, 100 meters of multimode fiber. You can see it still looks like a quality eye that you'd expect. Okay, so these are the standards. All of them, hopefully, you're familiar with. It's, the top is 10 gig for a single channel. You got 40 gig for bonded and 100 gig for bonded. That's the real challenge. Not only can you get one channel right, you have to get a group of 4 or a group of 10 bonded together and be able to perform all the logic it takes to bond those two and to basically fully terminate that and to get it aligned in your data path. So these are all the standards that you should imagine. Now, on top of these standards, we also support, of course, the other standards like PCI Express or HyperTransport or QPI or different standards. I was just focusing on the datacom standards for this particular example. And each one of these are existing today. They're shipping today. They're in testers today. And we're shipping and testing each of these platforms. So a couple examples. 100 gig. You typically would see interlocking, for example, in that last foil between an Ethernet MAC and a memory controller, a queue manager, and you have packet processing. So the ability to move traffic at 100 gig across FPGAs is a challenge. It's not completely solved. We can get the data in now. We can actually terminate it. We can do some amount of processing. We can move amazing amounts off to off-chip memory. We have 4 by 72 memory DDR3 interconnects, so there's a lot of bandwidth. And then we're innovating. We think that there was more coming for the ability to move out as much as you can off to novel types of DRAM, novel types of memory structures to get out as much as you can to be able to read a random packet out of your external memory at line rate. So that's the challenge. This is a challenge not just for FPGAs, it's a challenge for ASICs and anybody doing a packet processor or traffic manager. But one thing that's nice about FPGAs, they tend to have a lot of bandwidth, a lot of transceiver bandwidth, and a lot of user I/O bandwidth. We maximize to the package, and I think we're at the state of the art for the ability to connect to both memory and to be able to connect to the line rate. So another example here is an ONT4, where you once again have an optical module on both sides in this case, and you may be doing an Ethernet MAC. In the, basically forward error correction, it's all over the place. That's a beautiful thing for an FPGA. It gives you more reason to be able to not be able to do an ASIC. You can actually have a lot of differentiation by your end products with unique FECs. They may use their own polynomial. They may do something that's very unique to them. We love that. And then second of all, ONT4, I mean, that's coming. this product is today shipping in an ONT4 tester by JDSU. It's announced already. It was announced last week. And once again, FPGAs are first adopted by testers, second by the emulation market, and thirdly into the masses of various end products. Okay, so that's the high end. I talked about taking Stratix 4, moving it to 11 gig on all the transceivers, or at least a good portion of the transceivers. And then now I'll be talking about, well, that's expensive. That family is, $50 to $1,000. Now I'll be talking about the family that's, sort of $10 to $100. This is a family where we want to get down to the price point to be able to get in the masses and get available to more. And then there's another price point, just to put that in perspective, of sort of $1 to $20. And we have another family called Cyclone for that. So this is a mid-range product. It's a product that hits that sweet spot of $10 to $100. And what we did is we took the same fabric that you find in the Stratix 4 with the product you just saw. We actually do some optimizations, but architecture is the same. And when any IP that you develop in that architecture will work in this architecture. It still uses a 6-input LUT. It still has 2 registers per LUT. It can be fractionable. It still uses, ABB, advanced body biasing. It still uses the redundancy factors that we have in there. What we did is we really drove down the cost, particularly on getting to our value proposition, particularly on the I/O, the package that comes with that. This is the transceivers up here on the top. It's a complete ground-up design optimized for cost. Cost. And then also power. That's what this family is all about. And it says right here, for a reasonable amount of quantity, you can get it for $15 entry. And we'll probably continue on driving that down. So here's the family, a whole bunch of them. It scales from 16,000 logic elements up to 256. And just put that in context, the logic elements or logical cells is kind of a backwards calculation to the 4-input LUT you just heard about. And it's about, you take it times 12 for an ASIC gate equivalence. So it's about a 3 million gate ASIC type thing. The Stratix family I just talked about, that was up to 530, and we're moving that up to over 800,000 logic elements. So that'll be about 10 million gate ASIC. And then you have various resources on here for RAM blocks, 18 by 18 multipliers for algorithms like FFTs, different transceivers, and various PLLs that have been integrated on here. Once again, this is 40 nanometer, but low cost. We're driving down the cost of that. Okay, packaging. Commodity packaging. This, unlike the last presentation, was more targeted for the 1 millimeter pitch, typically like more wireless base stations, for example. They're typically more typical chassis that you'd find in ATX-like chassis. There's another market that's on our Cyclone line that's very fine pitch. We do take a 0.8 millimeter pitch here, but in general, it's 1 millimeter pitch, kind of commodity packaging. Try to drive the cost out of the packaging as much as possible. What you'll find in FPGAs is usually when you get into the design, you really don't know how big it's going to be and how much memory is going to be needed and how much logic is going to be needed. So we have vertical migrations. Usually you'll lay down your board, a 572-foot print, and then you have 6 deep vertical migration. In other words, you can scale anywhere in there. It's pin compatible. In the case of the hard copy, it not only goes to Stratix pin compatibility, it also goes to an ASIC compatibility. And then I always like to show an example. An example for this that's just being driven for cost, power, is the base stations. Base stations are just driving that. There's a few of them in the world now, and they're trying to get the cost and the power and the number of complexities actually going up. So here we've got to drive the cost down and double or triple the complexity that's being asked for as you go to LTE class platforms. The nice thing is the algorithms are changing. So once again, it's very good for FPGAs. The other thing that's nice is as you have your radio antennas up at the high end, you have to tune those MOSFETs and you have to save power. And so that enables you to keep a programmable device where you can actually tune those algorithms on an ongoing basis as you improve your algorithms, as well as different antennas and different structures at the top of your base station actually need to be optimized. So this is a beautiful place for FPGAs. It's a place that used to be both ASSPs and ASICs. It's a beautiful place for FPGAs. You often find a FPGA in the RF front end as well as in the base station part, or the baseband part of it. But it's once again, has to be under 5 watts. It has to be at a cost point. And it's equitable to that market. Okay. So I talked about the high end, Stratix. I was going to talk about the low end, which is the Arria 2 GX. And then I want to talk about software. And Chuck asked me from Microsoft, of course, the chair for our things, make sure you talk about software, because software is part of the innovation. What's happened in the EDA tools in the last 5 years is wonderful. The tools, I've recently used both tools, and they've improved dramatically. They've improved on many fronts. They're not just in synthesis. So incremental compile. The old days, the FPGA, where you had a little small FPGA, it's a flat design, are over. As you get to these larger devices, 10 million gate ASICs, you have to do incremental design, and you have to be able to and because that could give you productivity gains. You can be team-based, and you can do incremental compiles in certain portions of your design. And that actually enables us to do parallel processing better, which I'll talk about later. That's important for us to move forward on compile times. So the next thing is, how do we take care of multi-processing support? So I thought it'd be interesting to talk about that a little bit and talk about how our own EDA tools, as discussed yesterday for parallel computing, can be applied to that problem statement. How much have we been able to improve our compile time with parallelism? So we live for parallelism. We are a parallel platform. I'll talk about how the kind of improvements we've had for parallelism. Time quest, we've gone to more of an ASIC-like timing constraints, SDC. So it makes it more of a, between incremental compile and SDC, you actually are more of like an ASIC-like environment, which is a little bit novel and different from some of the FPGA design environments. Power, you know, how do you measure power in FPGA? I mean, a lot of innovations happen on the software, both in the accuracy of it, the ability to predict it in a stimulated environment, and give you early prediction as well as the synthesis tools actually being optimized for that. So we've done a lot of innovation on power play, making sure that your power design across the device has the integrity that it needs. Not only that, we also do a lot of things in SSN, so you can predict your SSN components and the risk factors you have relative to that. Significant improvement in the complete industry for that. SOPC, now that you have these big devices, how are you going to combine that IP? Now, in the industry, you can go to places like Xilinx or ARM and get networks on a chip. In the FPGA, you have to be a little more cautious. You have to be able to use the muxing in there in a more efficient way. And so we provide for you a tool that basically connects all that IP. And then signal tap, the ability to come in and you know, the FPGA is a tester, essentially. You can go in and use all that extra memory to do any kind of trace you need and be able to attach any unused pins to any kind of test element and be able to get the information out. And then when we get into compile time, we'll talk about how do we lower that memory. And I'll talk about that in the next slide. So let's look at parallel processing. Yesterday, we talked about parallel processing and the kind of gains we need to have to move forward. Now, this has nothing to do with FPGAs yet. This has to do with our EDA tools being applied, and we got to get down those compile times from many, many hours to fewer hours. And so what we do is we have to take advantage of 4 processors like in the Halem. And this shows you that as, you know, this is the logic density. And this shows you for 2 or 4 processors versus 1, the ability for us to drive down and improve for runtime improvement and get parallel processing. So I thought I would use an example for what we talked about yesterday. What kind of gains can we get? Now, it says for the total flow with 4 processors versus 1, it's about 16%. We've actually moved up to 30. This is a little bit of an old slide. So we get about 30% gain for parallel processing. Now, we haven't tackled every aspect. There's 4 aspects of sort of the EDA tools, if you want, going from synthesis to the back end. But just looking at synthesis, which we call MAP, you have 2 and 4 processors. We were able to get, you know, 1.9x, almost 2x. It came at a cost of memory, which is the next line. That's why that's green, that's red. Is that, yes, it took us more memory on our machine, which is not a good thing necessarily. We traded off memory to be able to process those threads. And we were able to get a 2x gain in that component of our synthesis. The nice thing about synthesis, the reason we started there is because it's blind to the customer. In other words, we can just take your tool. Now, it varies per design, but we can generically be able to move that across 4 processors. The other big gain is going to happen with incremental compile, where we break down your design, but that's design dependent, and that's not quite as prevalent in FPGAs yet. Okay, just an example of improvements in the EDA flow. So, in summary, the main thing I want to talk about was actually the 2 products. The first one, we took Stratix IV, and we moved it up to 11 gig, and we have that in production now. We have it in testers. We have it in the markets. Our fastest ramp ever to revenue, our fastest, largest design pipe, and it's our fastest execution to get a family out, which is pretty amazing for 40 nanometer. 40 nanometer, as you know, if you look, Red E times had a few bumps on yields. We didn't see any of that. We use our own design rules, which is a slight change from the TSMC design rules. We use design for manufacturing up front. We haven't had any issues on the yield with that. And then Arria 2, you know, FPGAs are great. There's only so many people who are going to buy an expensive FPGA. We have to drive down the cost to get the gains. If I look back at 2002 to now, we're going from, you know, a 1S80 to 800,000 logic elements. That's a big jump. That's a 10x gain since 2002. Performance has doubled. And the power for every generation in there, there's about 4 generations, has gone down by 50%. So I would say that we got a pretty good record. If you actually count the transistors going from here to there, it actually beats Moore's law. So I mean, we actually put more transistors on Moore's law, and we're able to do that at the same power profile from that 1S80 to which you're going to be coming up with a high density part is still under 25 watts plus I/O. You have to add the I/O back on. And then on the low cost side, you know, Arria, you know, the trick to that was getting down the cost on the delivery to our value. And I think everyone in this room that's doing silicon design, you have a value, whether it's a processor, an FPGA, or GPU, but the cost for the overhead of getting off the chip, such as your PCI Express or your memory devices, you have to lower that cost. And we did a lot of innovations on that. And part of that innovation is actually putting on hard IP. So for example, for PCI Express, we actually put a hard PCI Express MAC on. You'll hear more about that from various vendors. And I think the trend for FPGAs is that we will be putting more structures to bring down the cost of connecting our value proposition to the outside world. I think that's a general trend you'll see. And that's one of the ways we'll continue to innovate on giving more functionality per power by actually adding more functionality in. Wow, 4 minutes to go. So that gives you the opportunity for questions. So we're a little fast. Thank you. Thanks.
To be perfectly fair, I think they actually forgot to start the clock
Oh.
on time. So do we have any questions from the audience?
Al Wegener with Amplify. Dan, can you make any comments about how hard copy is being accepted in the market?
Well, we continue to do about a tape out a month, a tape out a week, which is pretty much industry class for any ASIC vendor. A tape out to us, by the way, is not a full layer change. Oh, sure. So it's you know, an all mask layer change is quite expensive. We just do 2 metals, 2 vias. So what you do is you take your FPGA and you move it to hard copy. So hard copy is not intended to be a huge market as proportion to the FPGA. We still think the core is in the FPGA value proposition. The value position actually goes up in the fact that you're able to do emulation or development, and you've got to get to that sort of price point that may be under $100. So here, when I said 2.5 billion transistors, we can take that down to 1/10 or 1/30 for the same functionality. But it's still, you know, close to more like a 10 to 20% of type of our business versus we don't see it as a mainstream. We see it as an enabler for Stratix customers to be able to have a path. The nice thing is that many people can get into FPGAs, do your design, and decide at a later date that they want to move to hard copy. So hopefully that answers your question.
Any other questions? Okay, thanks very much. Right, and since we are sticking with the usual suspects, we figured we'd round them all up, and our final speaker in this session is Peter Alfke. Let me ask you a question. How many of you people in the audience actually use FPGAs? Okay, and of those people, how many have never read an application note written by Peter Alfke? Effectively 0. Okay. Well, that's because Peter has been around for a long time. Peter was actually educated at the Technical University in Hanover, graduated in 1957, and worked on various telecoms and computer projects with Ericsson and Litton before moving to California in 1968. He spent about 40 years in application engineering with Fairchild, Xilinx, Zilog, AMD, and now Xilinx. He holds more than 30 patents and has authored, as I mentioned, many application notes. So Peter is going to tell us today about the Spartan and the Virtex 6. Peter?
Am I hooked up? Thanks for that friendly introduction. I've been around a few years, and in actual fact, I can let you in on a secret. You know, I'll retire next week after 52 years in this industry, so wish me luck. So, okay. Moore's law. Moore's law has been really good to Xilinx and Altera, you know, and it has been good to me because it allowed me to attend this conference and speak three times in a row about the newest families that we introduced, because we happen to introduce one family, you know, every other year. We double the capacity, same as Altera does, and compared to the previous generation, and that, of course, reduces the cost. So that comes almost free from Moore's law. What doesn't come free is speed and lower power. You know, for that we have to use what was called trickery yesterday. So that doesn't scale for free, but we're working very hard at it, and we have been reasonably successful. If you look at FPGAs, Xilinx FPGAs, they cover a very, very wide range. The largest Virtex 6 compared to the smallest Spartan 6 is a 250-to-1 ratio. So the Virtex 6 covers a 10-to-1 ratio, and Spartan covers a 40-to-1 ratio. So that's very different from what Intel does with microprocessors, for example, or even what the memory guys do. So we now share a common architecture between Virtex 6 and Spartan 6. That didn't used to be that way. You know, in the past, sometimes you thought, you know, is Virtex and Spartan really made by the same company? But it is, and it will be even more so in the future. So the difference between Virtex and Spartan is that Virtex emphasizes performance, speed, and large size, so density. And cost is important for everybody, but cost is secondary there. Whereas for Spartan, cost is everything, and low power is also everything. So both of these families, Virtex 6 and Spartan 6, they got the same name, the same numeric designation, and they both have been sampling since this year. It used to be that FPGAs were lookup tables and I/O, but now, of course, that's not true anymore. The new FPGAs are not your father's FPGAs anymore. They have a lot of hard IP blocks, and those hard IP blocks achieve the very high performance, they lower the power consumption, and they add flexibility to it. So we have significantly evolved the FPGAs over time. The hard IP blocks give higher speed and are more efficient, and they're easier to use. But we've got to be careful. You know, whenever we put a hard function into the chip, it means everybody has to pay for that function. And if somebody doesn't use it, you know, the customers look unhappy. Those that use it derive a significant benefit, you know, 10-to-1 sometimes. But we have to be careful that we don't overload it with stuff that people don't want. So it's a battle in the definition in every generation. What should be put on there? And here you see the list of all the various function, encryption, memory controllers, clock generations, and so on. So okay, it's horrible when people build up slides. So the structure of Virtex and Spartan is slightly different. In Virtex, all the I/O are scattered over the chip, and I'll show you later on how that gives us a better package. But the common resources are the lookup tables. Both of them are 6-input lookup tables, the block RAM, the DSP slices, 16 by
18 by 25-bit multipliers and accumulators, high-performance clocking. It's not exactly the same in both families, but similar, and parallel I/O. And both of them now have gigabit transceivers. The Virtex 6 has FIFO logic. The block RAMs in Virtex 6 can each be used as a FIFO with a hard FIFO controller, and we didn't do that in Spartan because not everybody needs it, and Spartan is very cost sensitive. And we have an Ethernet controller in Virtex, which we don't have in Spartan. The Spartan 6 have a hard memory controller, and I'll talk later about that, and they have 3.3 volt compatible I/O. 3.3 volt has become a high voltage standard that isn't necessarily compatible with very high performance chips. So let's talk about Virtex. Virtex is the next generation high performance FPGAs from Xilinx. It's built on a 40 nanometer process, and compared to Virtex 5, it is somewhat evolutionary. It increases the size, it doubles the size, and increases therefore the density, and it potentially reduces the cost compared to Virtex 5. It will reduce the cost. The speed is increased, and I'll show you some details later on, and the power consumption is reduced, but that was due to hard work because, as I mentioned before, it doesn't really come free with Moore's law anymore. So you have to do something to the architecture and the circuitry and a lot of what was called trickery. There are features are usually in Virtex 6 are evolved from Virtex 5. So we divide the family into 3 subfamilies or platforms. LXT is the base version, but it has also serial connectivity, multi-gigabit transceivers. That's what the T stands for. The SXT is fundamentally the same chip, but it has the same features, but it has a different mix. It has more multiplier accumulators, and it has more memory. So it was made for single processing applications, but it is essentially the same structure. My standard joke was one of them is gin and tonic, and the other one is tonic and gin. So the HXT is a new family that adds 11 gigabit transceivers to the mix. So the rollout is staged. The LXT and SXT are coming out now in ES versions, and I'll talk later about availability, and the HXT is for early next year. So the power consumption is a very important aspect of FPGAs, as high performance FPGAs especially. So we've worked very hard to reduce static power, which essentially means we have to reduce the leakage. And we introduced triple oxide several generations ago. So this is the 3rd generation that uses triple oxide, so that we have fast transistors when we want transistors to be fast, when they need to be fast, and when they don't need to be fast, for example, all the configuration transistors don't have to be fast, then we use a different threshold, what is it? A thicker oxide, different oxide thickness, and therefore achieve considerable lower leakage current. And so the idea is to achieve speed where you need it, and achieve low leakage current where you don't need the speed. On top of that, we use silicon germanium and strained silicon and all the today normal tricks to reduce static power. Dynamic power you reduce by shrinking the geometry so that the circuitry gets smaller, the capacitances are smaller, and use low-K dielectric material in the interconnect. So instead of using normal silicon dioxide, which is an epsilon of 4, you go down to something slightly lower than 3. So, and also we can achieve lower dynamic power consumption by reducing the supply voltage. And the VCC is down to 1.0 volt. And there is a version of these chips that uses 0.9 volts, just 10% less, which gives you 20% lower dynamic power consumption at a slightly reduced performance, slightly reduced speed. So, talking about performance, if you compare Virtex 6 against Virtex 5, it's against our own family, so we can be really fair and honest there. Don't have to compare ourselves against a competitor. So we have the logic itself is about 15% faster. And that's partly due to the process, partly due to reduced routing, partly due to better pipelining options. I'll talk about that a little bit later. The serial transceivers have a considerably higher bandwidth, almost double, because we have up to 72 transceivers now, and so the total aggregate bandwidth is 580 gigabit per second. Sounds good. And compare that to 48 transceivers, a smaller number of transceivers in Virtex 5, delivering at slightly over 300 gigabits per second. The general purpose I/O is 33% faster, and clocking is about 10% faster, and the DSP bandwidth has more than doubled. So we're faster than we were in Virtex 5, and there's nothing wrong about Virtex 5 because it's a very successful family. Ease of use is another aspect that we have to work on. So we have made sure that Virtex 6 is backwards compatible with Virtex 5. So most of the features are very similar, and designs can be ported from Virtex 5 to Virtex 6. I/O planning is simple because it's our religion that all I/O should be the same. So every I/O has the same features in every bank. You can decide on the supply voltage, but the fundamental feature of every bank, every I/O pin are the same. The power supplies, you can get away with as little as 3 power supplies, and that's very desirable to simplify your PC board. And all of that gives you a shorter time to market. The logic, lookup tables, it's a 6-LUT that we had in Virtex 5, but we gave it 2 transistors, 2 flip-flops. So both outputs from the Virtex 6 LUT have a flip-flop, which essentially doubles the number of flip-flops in Virtex 6 and Spartan 6 compared to the previous generation. So that makes pipelining considerably easier. The block RAM is essentially a copy of what we had in Virtex 5, so don't tamper with success. Clocking is significantly changed, and the problem is when you have a large chip and you want to clock at a high speed, you have to stretch that clock over a large area. That's not that easy. So very large chips need very sophisticated and cleverly designed clock trees, and we've done that. We've improved the clock distribution. We've also improved the clock generation. And in the area of DSP, multiplier accumulators, we significantly increased the number, and we also increased the speed by a little trick of giving the multiplier a pre-adder in it that significantly increased performance. It seems to be an innocent little thing, but it has a significant impact on the speed. Select I/O, which is the general purpose I/O, is faster. LVDS runs at 1.4 gigabit per second now, and we can interface to DDR3 and support lots of different memories. The GTX transceivers run 6.5 gigabit per second, and the faster ones will run 11 gigabits per second in the GTH. So there are dedicated blocks for very fast I/O. PCI Express is a very popular feature. So it supports now 5 gigabit per second, for Gen 2, and it has special wrappers for endpoint implementation. And the EMAC, the Ethernet controller, is somewhat similar to what we had in the Virtex 5 generation. We have paid a lot of attention to signal integrity issues. Virtex 6 uses flip chip exclusively. All Virtex 6 chips and Virtex 5 use flip chip technology, which means we spread the I/O over the chip. The I/O is no longer just around the periphery of the chip, and we have up to 8,000 bumps. I'll show you in the next picture on the next slide. We put decoupling capacitors in the package right next to the chip, which means they are where they belong and where they do best, and they are special quality capacitors with very low series inductance and resistance. And we have a 10-layer controlled impedance package. You can see that here. So the chip is here, the silicon is here. It has it's flip chip, so it's sunny side down. The active area of the chip is down here. On the back is a heatsink, metal heatsink. Then it connects to a 10-layer, about 10-layer package, which is a PC board. And the connectivity is with bumps, up to 8,000 bumps. So the bumps are directly on the chip, and they connect to the package. This is the package, which is another 10-layer PC board. And then the balls with the 1 millimeter pitch come here, and your PC board comes down here. So I used to joke, say that there's about 10 layers of routing on the chip. There's about 10 layers of routing in the package substrate, and there's at least 10, there's often 10 and more layers of routing in your PC board. So the electrons get a little bit dizzy. So I was talking about Virtex 6, which is our high-end family. Even the Spartan 6 family, which is our cost-sensitive, lower performance, lower cost family, it uses a 45 nanometer process and is optimized for low cost and low power. And usually in the low cost world and low power world, the features are simpler and slower, but there are exceptions, you know. And the exception is a DDR3 controller, hardwired, macro in the Spartan device, and a multi-gigabit transceiver. And let's look at that in a little bit more detail. So there are up to four DDR3 controller hard macros on the chip. Why did we do that? Why did we put a very high performance DDR3 controller in Spartan when we didn't do it in Virtex? Well, Virtex has a very fast fabric, and Virtex can retain its flexibility and still implement a hard memory controller. But Spartan needs to interface to external memory. And the strange thing is, the lowest cost external memory is DDR3, and DDR3, because it has PLLs on the memory chip, cannot run slow. So it cannot run below 300 megahertz. So in order to put a low-cost external memory on a low-cost FPGA, you have to run fast, 300 or 400 megahertz. And that is borderline impossible with the existing fabric. So we decided to give it its own dedicated controller. So here's a picture of that controller. It has an interface to the chip, and it does the usual things that memory controllers do. It calibrates for timing, it calibrates for termination, it provides the hard electrical interface, the PHY here. Then it has data path, it has FIFOs, it has multiple ports on this side, and a control structure that can handle these multiple ports. So anybody that has ever designed a memory controller will recognize most of these features. But the nice thing is they are hardwired in the Spartan device. Multi-gigabit transceivers, you will recognize this drawing. It is very similar to what we had in Virtex 5, but now we have it in the low-cost Spartan family. So it's 2 wires for the transmitter, 2 wires for the receiver, and the usual features that you expect in a multi-gigabit transceiver, and the previous speaker has gone into a lot of detail about how multi-gigabit transceivers work. So let's talk a little bit about availability. There are, because everybody asks, when can I get it? How can I get it? Where can I order it? I look at 3 levels of availability. The initial ES silicon. ES, some people think, stands for engineering samples. In my mind, it stands for early silicon. The first ES parts are used inside Xilinx to evaluate the chip and to characterize the chip and to build some evaluation boards. And they hardly ever go out to customers. Perhaps in a few cases they do. Then comes general availability of early silicon, ES. And so you can order those things through the distributor, and they usually have an errata sheet. They usually is something that isn't exactly like the user guide says or like the original data sheet says. But we're honest about that, and we can give you an errata sheet. In the 3rd quarter of 2009, you can buy this Spartan 6 LX16 and the LX45, so that's 2 parts in the Spartan family, and you can get the LX240T in Virtex. So 3rd quarter is just about, we're just about in the middle of it. The production then are parts that are 100% tested, that don't have an errata sheet, and you order them through distribution, and that will happen towards the end of this year and early next year. So let's summarize. Both of these families take advantage of 40 or 45 nanometer technologies from 2 different factories, actually, and have the common innovative architecture and circuit design. So they improve performance, they are smaller in chip size, they're lower cost, and use lower power. Virtex 6 is an evolution from Virtex 5 in many respects. It has very similar features, but everything is slightly improved and made faster, especially, and smaller, and there's more of it. Whereas Virtex 6 really did not evolve. Spartan 6 did not evolve from Spartan 3. We made a conscious effort to make Spartan 6 similar to Virtex 6. So the 2 families, they used to be cousins, and they're now brother and sister. So you will find a stronger commonality. It's easier for us to support. It's easier for you to design with. It's very much easier for you to move from one to the other. So they're similar in architecture, but each of them is optimized its own way. Virtex 6 is for performance, features, and capacity, size, 780,000 LUTs. So 10 times more than in the original Virtex 8-9 years ago. And in Spartan 6, low cost and low power consumption is the overriding concern. There is documentation on the web, data sheets, user guides. There are evaluation boards coming out, and there is software available. So, and when I put these slides together, I wasn't quite sure that I would retire, but by now I know.
Okay, thank you very much, Peter. I think we have some time for questions from the audience, and I will preempt the Mike and ask the first one. I noticed one thing is missing from the Spartan and Virtex families, and that's the Power PCs. What happened?
You have to ask nasty questions. There is no Power PC in this family. Well, there is no Power PC in the Virtex 6 family. So we rely on soft processors at least for the time being.
Yeah, that's fine with me. Over there.
Ilya Ganusov, Acronic Semiconductor. You mentioned that the performance of your SerDes and IOs increased anywhere between 80 and 30%, but the logic, even after a lot of hard work, only increased by 15. So do you think for a larger class of applications that would leave core as a bottleneck, which would not be able to take full advantage of fast IOs?
Well, I was talking about a relative increase in performance. And if you say the I/O increases more than the fabric increased, that would be a problem if they were perfectly matched before. And not everybody will use the high performance I/O at their top speed, 1.4 gigabit per second, for example. And not everybody will use the pipelining that gives you a higher performance in the fabric. So I think these numbers are not that hard coupled as you imply that they are. We make the fabric as fast as we can do, and I think the larger number of flip-flops that we have will allow you to pipeline more, we made it as fast as we could make it.
Thank you.
Just a quick question about the manufacturing of the Virtex 6 and the Spartan 6. Which fabs, which foundries are used to make them?
Okay, so Virtex 6 is at UMC, and Spartan 6 is at Korea. What's it? Samsung. Yeah. No wonder I'm retiring.
Don't worry, we're both in the same boat, Peter. Thank you very much.